Hi everyone, in this lecture we will talk about binary search, which is an efficient way to search in sorted arrays and lot more. So the advanced use cases I will discuss in the algorithms part, but as of now we are going to talk about how you can use binary search to efficiently search an element in a given array, and that array must be sorted, only then you can apply this algorithm. So the question is like this: so given this array and this is a sorted array, you want to find a particular element. For example, the someone asks you to find if 3 is present in this array or not. Okay, so we are interested in knowing the index of the element 3. Okay, so let's say the key in this case is 3. Okay, now you might ask how you can do this thing. Okay, so one way is you can do linear search, but a more efficient, a more better way is to use binary search. So in binary search, what we will do, we know the starting point of the array, we also know the ending point of the array, and we need to divide this array into two parts. Okay, so 0 1 2 3 4. So clearly you have 9 elements, so you will first find the middlemost element. So this is the middlemost element. So how do you find mid? So mid is nothing but the this start plus end upon 2. So once you know the middle element is 7 and the element you are looking for is 3, clearly you can discard all the elements which are greater than equal to the middle element, because since the array is sorted, it is not possible to have an element 3 which will lie after 7. So you can directly discard this much part of the array. And maybe let me just change this element to 2, because that would be a more better case. So now what you will do, or let me change this element as 5. Okay, so you want to search for the element 5. Okay, so what you will do now, 5 is less than 7. Okay, and it will not be on the right hand side of 7. Okay, so you just discard this much part and you shift your end to mid minus 1. Okay, so you change your end that now I will search in the smaller part of the array. So this technique is also called divide and conquer, where you break the array into multiple parts and you try to search for the array in a smaller search for the element in a smaller part of the array. Okay, so now the question is, we want to search for 5 only this much part of the array. Okay, and what we will do, we will repeat the same procedure. So we will find out the mid. So mid is going to be 0 plus 3 upon 2, that is going to be 3 by 2, that is 1. So this is going to be the middlemost element. Okay, and now we know the middle element is 2 and the key that we are searching is 3. So that means we have to discard all elements which are less than equal to mid. So we will just search in the right hand side part. So what we will do, we will move our start pointer to this place. Okay, so this is now the new start and we already have the new end. Okay, so this all goes off and this is now the starting. So what we will do now, so we have start which is pointing to 3, we have end which is pointing to 5. So we will again find out the middle element. Okay, so middle is going to be 2 plus 3 by 2, which is 5 by 2, that is again 2. So you say, okay, this position is my middle element, and in this case the middle element is 3 and key that we wanted to 5 is 5. Okay, so we want to search for 5. So what you will do, you will again discard the middle part. You will discard everything that is on the left of middle. So you discard this part and you make your start equal to mid plus 1. Okay, so that basically brings start to this particular point and this goes off and you again find out the midpoint. So what is the midpoint now? So midpoint is now 5 by 3 plus 3 by 2. So that is actually 3. So you see, okay, the middle element is 5 and key is also 5. So which means your middle and key are equal, and that, okay, so middle is 3 and this array of middle is 5. Okay, this is what I'm trying to say here. Array of middle is 5 and that is equal to the key that you are searching for. So you can just return the value of m, that is 3. So 5 is present at the third index. Okay, so this is how binary search is going to work. Okay, suppose the element was 6. So till now all the elements would have been same. Now you will try to search for 6. So what you will do, you will say Okay, till now you know the element that you are finding is 6, so the key is 6, but currently you are at 5. So what you will do now? Okay, so you will try to discard, you will try to move in the right direction. Okay, so right direction means this, so you will just start equal to mid plus 1, so your start will come to this place. Okay, so this you do when your middle element is actually smaller than the key. Okay, so middle element is smaller than the key, then you execute this step, and if the middle element is greater than the key, then you bring end equal to mid minus 1. Okay, so these are two important instructions that you execute. So in this case you will bring start at this place. So once this happens, you can see start becomes greater than end. Okay, so in an array, start should be always less than equal to end, but if start overshoots end, in this case it means you have tried for all elements and such a element does not exist. So clearly you can say this element does not exist. So this is the whole idea of binary search, and now we will see the implementation of binary search algorithm. And as I said, it is more efficient than linear search, and how much efficient it is, that we will discuss when we talk about space and time complexity. Okay, so let's get into the code. Okay, so we are talking about now binary search. Okay, so what I will do, I will just take the input from the linear search one. Okay, so let me just copy this much part from the linear search, so that we have at least the array as the input. Okay, so we have the array as input, and this time we will define a function called binary search. So this will accept one array. So this is how you actually pass an array to a function, and there is another way, you can also write it like this. More details will come later on. And second thing is, you have to send how many elements this array is going to have. Okay, or you have to send the starting point and the ending point of the array. So this is how you can pass an array to a function. Okay, so in this function we are going to write binary search. So okay, we can also do this thing. Okay, you send the array and you also send the number of elements, and you can say starting point will be 0, the ending point of the array will be nothing but n minus 1, and we will do something. Okay, while start is less than equal to end, because once the start becomes greater than equal to end, greater than end, we say that such an element is not present in the array. So we can return something to denote the element is not present. So you can just say return -1 if the element is not present. So first thing that you will do is you will find out the midpoint. The midpoint would be start plus end upon 2, and here you compare if array of mid equals to the key. Okay, another thing that you need to find pass is key. So if you find the key at the midpoint, so you can just say my answer is the midpoint. Otherwise, if array of mid is greater than key, which means let's say you are looking for a number 8, and currently at your midpoint you are at 5. Okay, that means 8 will be present in this part, so start needs to move to this point. So start will come to mid plus 1. Okay, and if you're looking for a number 2 and currently you are at 5, so looking for 2, so 2 will be present in this part, so you need to bring your end to mid minus 1. So in this case end will be mid minus 1. So the first case is if mid is greater than key. Okay, so mid is greater than key, so this case, so end will be shrink, so end equal to mid minus 1. So let us update our end equal to mid minus 1, else we can say okay, let's do else you can just start equal to mid plus 1. That's it, and this is it. Okay, this is the complete code of binary search, and this is going to exactly function in the way that we have discussed just now. Okay, so return -1 will execute if we come out of the loop and the element is not present, and here we can call binary search function. Okay, so we can say cout binary search of whatever is the array, what is the number of elements in the array, and whatever is my key. That's it, and let's try to run our code now. Okay. So let me give, there are, let's say, 8 elements, and these elements are 1 2 3 4, 10 20 30 and 40. And let's say I want to search for 30. You can see it is present at element at index 6. So 0 1 2 3 4 5 and 6. So this is how binary search works. And maybe one more case where the element is not present. Let's say I want to search for 10, so it says -1, which means the element is not present. So that's all, guys. I hope you would uh, apply binary search also to search in a sorted array. Thanks a lot. We will discuss more problems in coming videos. Hi everyone, so in this video we will discuss one use case of binary search to find the first and the last occurrence of an element in a sorted array. Okay, for example, you are given an array like this. You have numbers like 1 2 5 8 8 8 8 and let's say 10 12 15. So you are interested in finding out what is the first time that an element is occurring and where is the last time that particular element is occurring. So let's say our key is 8, and let's say this is our start of the array, and let's say this is the end of the array. Okay, so if you just apply the binary search algorithm, you will see you will get a midpoint. Let's say 0 1 2 3 4 5 6 7 8. So the midpoint is 4, but at this midpoint this key is present, but this is not the first occurrence of this particular key. So let us first focus on the first occurrence, that is this particular index. Okay, so what you can do is you can see, if you have array of mid, let's say this is array, and if you see array of mid, this is exactly equal to the key. Okay, so array of mid is exactly equal to key. In such a case, what you can do is you can note down this index. Okay, so you note down that at least you have a occurrence at this particular index, that is 4. So you say okay, you have answer that is the index 4, but it is also possible that if you're interested in finding the first occurrence, and let's say this index is your mid, it is also likely that if 8 is repeating, it must be present in the left hand side of this particular index. Okay, so what you need to do, you need to uh, search in the left part of the array. Okay, so do not stop at this point. Instead, you try to search in the left part of an array. So you just discard this part of the array and you say okay, my end will come to this index. Okay, so now this is the ending index, and what you will do, you will say okay, end equal to mid minus 1. Okay, so this is what you do. So you say okay, answer equals to mid and end equal to mid minus 1. So this is what you do. Now when end is at this point, you again find out the midpoint. So that, let's say this is the midpoint now. Okay, and now your mid array of mid is equal to 2, that is actually less than key. Okay, so if this is less than key, what you need to do, you need to make your start to mid plus 1. So you discard this part of the array. So you say okay, if this is the case, I will say start will become equal to mid plus 1. Okay, and there can be a case when array of mid is greater than key. Okay, for example, you are searching for a element, let's say 2, and at the midpoint, let's say this is the midpoint, let's say you have a 2 here, you have a 3 here, you have a 5 here, you are 8 8 8 8. Okay, let's say you have a midpoint where the element is greater than the element you are searching for. In such a case, you also have to make your end come to this particular position. So end will come to mid minus 1. So that will be another case. So end equal to mid minus 1. Okay, so you can see this is actually very similar to binary search, except this case. So this case basically says do not stop when you have found the element. Okay, don't stop when you have found the element. Okay, Instead, if you want to get the first occurrence, you start exploring left part of the array and left of the mid. And if you want to get the last occurrence of the array, okay, so the only change we will make is you start exploring the right part of the array. Okay, that's what you will do in the last occurrence. Okay, so let's with this, let's try to write the same thing in the form of a code now. Okay, so what I will do is I will make a function called lower bound, or let's say the first occurrence. So I will get the array, I will get the number of elements in the array, and I will also get the key. So let's say we have a start index that is 0, we have an end index that is n minus 1, and we have an answer that is initially not known to us. So we will always update our answer variable in a direction that the index is getting lower and lower. Okay, so update in a direction that answer value gets lower and lower. That will help us to ensure that we are actually finding the first occurrence of that element. Okay, so while there is at least one element in the array, so start is less than equal to end, you can find out the midpoint. So int mid equals to start plus end upon 2. Okay, and you can see if array of mid is equal to key. If this is the case, then you have to actually do two things. So do not stop at this point. So first note down that you have at least one index where this key is present. Okay, so answer is equal to mid. Okay, and then you can say equals to mid minus 1. Okay, otherwise you can see else if array of mid is greater than key. So that would mean you have to bring your end to mid minus 1, and one final case is left. When array of mid is smaller than key, then you have to say start equals to mid plus 1. Okay, so this way we are dividing our problem into two parts, and the final value of the answer will be the first occurrence. Okay, so that's how we can write the logic for the first occurrence. And if you want to try this out, I can say cout first occurrence of uh, of the number key in the array. So I give array and key. Okay, so if I give 8 as a my number, so I should get 0 1 2 and 3 as my first occurrence. Okay, so let's try to run this code. Okay, so 3 is my first occurrence. So similar logic we can write for the last occurrence. So I will just copy this code, and what will change in the last occurrence is this condition, that if the element is equal, so instead of exploring the left part, you explore the right hand side of that particular element. So you can say start equals to mid plus 1, that is do not stop but explore the right part of the array, because it is possible that if the element is repeating, then the occurrences will be in the right hand part. Okay, and since we are want the last occurrence, there is no point of exploring the left hand part of that particular array. Okay, so that's the change we need to make. So let's also see out the last occurrence. So if I give the number as 3, okay, 3 is not present in the array, so that means element is not present. And if I give 8, then I get 3 and 7. Okay, so that means this index should be 7. So 7 6 5 4 3 2 1 0. Yes, so this is the 7th index, and this is how we are able to solve this problem. Okay, so if you want to dry run this, I can do it. I can just do the dry run for the last occurrence part as well. So this is my array: 1 2 5 8 8 8 8 8 10 12 15. Okay, so it's 0 1 2 3 4 5 6 7 8 9 10. So the midpoint is this particular element. So when I come to this midpoint, I store that my answer is at least 5, and I discard this part of the array because if you want the last occurrence, it must be on the right. So I make my start equal to mid plus 1. So start comes to this point, end is at this point. Again, I find out the midpoint, it is this particular index, and at this index I know that I have the value 10. So array of mid is greater than key, so I make end equal to mid minus 1. So end comes to this particular position. So what I do, I discard this part of the array now, and I see what's the midpoint now. So midpoint is now this point, and I see at this index I again have array of mid equal to key. So I update my answer and make it as 6, because we are updating my answer in a increasing order. Okay, so answer will always increase so that we will get the rightmost occurrence. So what we do now is we again do this thing, start equal to mid plus 1. So we basically discard this part of the array, and now start is at this particular point. So again we find out the mid, that is 7, and you can see this answer will get updated, that is as 7, and we again make start equal to mid plus 1. So start will come at this point and my end will be at this point, and at this point when start has crossed the value of end, our while loop will stop. Okay, and we will return the answer that is at exactly 7. Okay, so the same logic goes for the lower bound as well. So that's the only line that we need to change. Okay, so I hope you got the logic and you will be able to write the solution on your own. Hi everyone, in this lecture we will see how to find an element occurrence in a sorted array. Okay, so we can use the find function, but it is slightly inefficient. If the array is a sorted one, we can use binary search that works in order of log n time. So instead of making our own binary search function, we will use a function that is available with the C++ STL. So you can say bool present equals to binary underscore search. So this function returns true or false depending upon element is present or not. So you want to search in this particular array starting from 0 till the n minus 1 index, and here you will give the key, what is the element you want to search, and you can check if this is present. You can say cout present, else you can say it's absent. This is as simple as that. Okay, so we are making this function call that is provided by the algorithm header file. Okay, so let's give in some input. So if we give, let's say, element 100, we will get if this element is present or not. So 100 is present, and if I give, let's say, 140, then this element is absent in this array. Okay, so this is how easy it is to use the binary search function. And two more things I want to discuss in this video. One is, suppose you want to get the index of the element, okay, where this is present. So for that, the algorithm header file provides us with two functions. One function is called lower bound, where you give the start and the key, and another function is called upper bound, where you also give start and the key. So let us try to use the lower bound function. So these functions actually return the address where the element is stored, and we are calling that variable as iterator. Okay, you can make it of the type int star, but I'm just making it auto because it's an address of a bucket inside the array. We can just make it like this as well. Okay, so let me call auto it, and we are going to call lower bound function on this array. Okay, so this is array, and let's try to search for the lower bound of the number 40. Okay, so let's say this number is 40. Okay, so what does lower bound will return? A lower bound function will return me the address of the first bucket that is greater than or equal to key. Okay, so this is my key. So it will give me the first element that compares greater than or equal to key. So in our case, we do have the number 40 in the array, and the index of the first occurrence of 40 is 2. So we should get the address of the bucket 2. And if you want to get the index, you can simply say it minus arr. That is going to give you the second index. So let us see if we get the index 2. Okay, so yeah, we are getting this thing. So we are getting the output as 2. Okay, let me say this is lower bound of 40. And what about upper bound? If you want to see what is the first number that is greater than 2, lower bound of 40 is 2. Okay, so let us also discuss how to use the upper bound method. So the function call is very similar. So instead of calling lower bound, we will call upper bound. So remember, this lower bound is going to give you the first element that is greater than equal to key, and upper bound is going to give you the first element that is strictly greater than key. Okay, so let us have a look at the occurrence of first element that is greater than key. So this element is going to be 50. So if you calculate this index, this is going to be 0, 1, 2, 3, 4 and 5. So upper bound is going to give you 5, lower bound is going to give you index 2, and if you subtract upper bound minus lower bound, you are going to get this number of elements, that is 5 minus 2, that is 3. Okay, so suppose the question is you want to find frequency of an element in a sorted array. Okay, if you want to do this, so clearly this can be done using 5 minus 2, that is 3. The number of elements will be equal to 3 in this particular array. So let's do another thing. Okay, so cout upper bound is this, cout occurrences of 40 are, or you can say occurrence frequency of 40 is upper bound minus lower bound. So maybe upper bound, let's call it lower bound, and here we say okay, lower bound minus array, upper bound minus array, and we can say this is nothing but upper bound minus lower bound. That's it. And you can see we can just find occurrence of this any number in logarithmic time, because both upper bound and the lower bound functions, they work in log n time. So let's see the output. So occurrence frequency of 40 is equal to 3, and you can also verify if an element is not present. Okay, so you can say if a lower bound equals to n in this case, or lower bound minus this thing, array index. Okay, if this is equal to n, you can say element is not present. Cout element is not present. So if I make this element as 41, so this is not present, and you will see this thing. Okay, okay, we if you give 41, then you will get the next element, that is 50. Okay, so lower bound in this case will give us 50, lower bound of 40 is 5, because it gives us the first element that is greater than equal to key. So if you want to check if the element is present or not, you first make a call to binary search function, that you should do. Okay, so you will get this. So lower bound of what is 5, so you're getting 0, 1, 2, 3, 4 and 5. Okay, so this is what you will get. And occurrence frequency of what is 50, because in such a case both lower bound and upper bound will be same. Okay, so you actually do not need to do this thing. Either you can check the frequency or you can check, but yeah. Okay, so you should ideally use binary search to check if an element is present or not, and if it is present then you can use the lower bound method to check where it is present for the first time. Okay, so that's all for this video, and we will talk about more concepts in the next video. Hi everyone, so today we will discuss the problem Help Rahul, that is the 10th problem from 10 days of code series. So in this problem you're given you have to apply binary search on a sorted and a rotated array. Okay, so its problem is very straightforward. So it says Rahul had a sorted array of numbers, his friend rotates the array. Okay, so for example, if the original array was like this, so due to rotation this array becomes something like this: 4 5 1 2 3, and you have to find for a particular number. For example, you want to search for 2, so 2 is lying at this particular index, so you want to do it efficiently. So instead of using linear search, we will think in terms of binary search. So let us see how we can solve this problem now. Okay, so what I will do, I will show you how you can apply binary search on a sorted rotated array. This is what we are going to do. So okay, let's discuss this problem here only. So for example, the problem rotated array is like this: 4 5 1 2 3, and if you try to map these values on a graph, you will see the graph will look something like this. Okay, and suppose these numbers are 1 2 3 and these numbers are 4 5, so this is how it will look like. And if the array would have been completely sorted, then it would have been like this. So this is not the case, this is the case. So in binary search we clearly know that the very first step is to find out the midpoint of the array. Okay, so suppose if you find the midpoint of the array on this, the midpoint will lie either on this curve, this part of the array, or on this part of the array. Okay, so we do not know where this midpoint will lie, but clearly there are two options. So suppose this is the option 1 and this is the option 2. Okay, so we will make two cases, one for option 1. So how do we know the midpoint lies at this particular point? So clearly if midpoint lies on this particular point, this array will be sorted. Okay, this array will be sorted, and we can check if because there are two parts of the array now. Okay, so this is part 1 of the array and this is part 2 of the array. Part 2 will not be sorted, part 1 will be sorted if midpoint lies on the first part of the array. So in order to check this part is sorted, we can check if array of start is less than equal to array of mid. So if this is the case, we clearly know this part of the array is sorted, and again we can search for the element in this part or in this part. So when we will go in part 1, so we will go in part 1 if your key element that you want to search lies in this particular range, if this element lies in array of start and array of mid. Okay, so we will reduce our problem size to this part if the key element lies in this particular part. Otherwise we will say, okay, it does not lie in part 1, let us search for the element in part 2. Otherwise we can say we will make a call on the range mid plus 1 to end. Okay, so we'll start in search in the range start to mid. If the element lies in this particular range, if it does not, we will search in part 2. Okay, the other option is midpoint of the array lies on this part. Okay, so if it lies on this part of the array will be sorted. Okay, so this is now part 1, or let's say this is part 2 and this is part 1. So this, and if you want to check where does the element lie, does it lie on the right or does it lie on the left of the mid, so you can clearly check if the second part of the array is sorted. So how do you check if the second part is sorted? So in that case, you can either make a put a if condition here, and you can put a else condition here, or still if you want to check, you can see for this part of the array, array of end will be greater than equal to array of mid. So this will be the condition in this case. Okay, so if this is the case, again you want to know, okay, you came to know this part of the array is actually sorted. So where does the element lie now? So if this part is sorted, you can check if it lies in this part. If it doesn't, it will lie in this part of the array. So you can check if your key lies in the range array of mid and array of end. Okay, then you will search in this part. Otherwise you can search in the first part of the array. Okay, so else you can say search in the first part of the array, that is from start to mid minus 1, something like this. Okay, so this is what we are going to do. So it makes a total of 4 cases. Okay, so why 4 cases? First 2 cases for the midpoint, where does the midpoint lie, and 2 cases for the element, does it lie to the left of the midpoint or it lies to the right of the midpoint. Okay, so we are making these 4 cases because there is a break. Okay, so this is not a sorted array, this is a sorted and rotated array. So this is what we are going to quickly solve do in this video. Okay, so let me just write the same thing in the code now. Okay, so we will have input n and array. Okay, what we will do now is we will write a function. Okay, we will also accept key. So let me check from HackerBox, where is the key? Okay, we have to output -1 if the number is not found. Next line contains, okay, the final line contains the item to be searched. So okay, we can say int key, scene key, and here we will write the function to find the element. So let's say int find, int array, int and int key. So in the beginning I can say start equals to 0, end equals to n minus 1, while start is less than equal to end. We will find out the midpoint. Mid is given by start plus end by 2. And what we will do now is we will check if the array of mid equals to key. So this is one special case. So if the element is found, we will just return mid. Otherwise we will see if the, or we can say else if, okay, array of start is less than equal to array of mid. That means we are talking about the midpoint lying on the first part of the line. Okay, so here we will have 2 cases. We have to check whether the element lies on the left or on the right of the mid. Okay, so this is the case when you have this line. Okay, so mid lies somewhere here, and clearly this part of the array will be sorted. The remaining part of the array will not be sorted. This will be unsorted. So you can check if mid, if the key element lies in this range. If this lies, then you search in this part. Otherwise you search in the other part. Okay, so if key is greater than equal to array of start and key is less than equal to array of mid, then you search in this particular part. So how do you search? So you can say end equals to mid minus 1. Otherwise you can say search in the other part of the array. So start becomes equal to mid plus 1. So this is one case, okay. And another case is your key lies in the other part of your midpoint lies in the other part of the array. So let me show you now. So if we are talking about this case, so if mid lies on this line, this part of the array will be sorted, and here you can check if the key element lies in this sorted array, then you bring your start at this point, start equals to mid plus 1. Otherwise you say no, it lies in this particular part, so you bring your end equal to mid minus 1. So this is what we are going to do. So else, if key is greater than equal to array of mid and key is less than equal to array of end, we can say start equals to mid plus 1. Else we can say end equal to mid minus 1. So this is it, and finally we can say return minus 1 if the element is not found. So from here I can say return minus 1. So let us try to test our code now. So let's say 5 elements. Okay, we should also take input n. 5 elements, 4 5 1 2 3. I want to search the index of 2. So I forgot to make the function call cout find, or let's say find key. I give a and key. So it is, let's say 4 5 1 2 3. So second element 2 is present at third index. Let's search for okay, so 1 is present at 0th index. So this is fine. Okay, so let's try to submit our code on HackerBlocks and see. So waiting for the results. Okay, so this is how we could solve this problem, and as you can see, this was a clearly straightforward application of binary search, and it was also mentioned in the hint you have to solve this problem using binary search. So I hope guys you have understood this problem now and how you can modify binary search, and the reason why you should use binary search is it works in a logarithmic complexity as compared to linear search, and it's very fast. Okay, so for large test cases this is definitely going to help you. So thanks a lot, see you guys in the next video. Hi everyone, in this video we will discuss one problem that's based upon binary search, and we will also learn a new way to approach binary search problems. Okay, so I'm going to teach you a technique that is going to apply to most of the questions that are done using binary search. Okay, so let's see how do we find square root of a number, and we will also learn about this technique side by side. Okay, so for example, you are given a number n and you want to find the square root of n. Let's say this is 3. So as of now I'm just talking about the integer or the floor part. Okay, so we are taking the floor. So what you need to do is given this input you need to find out the square root. Okay, you cannot use any library function, and we are not going to use brute force because it's going to be inefficient. So what we can do is we actually have to think of a search space. Okay, so in any binary search problem you have to think of a search space. So clearly in this problem you are not given any sorted array. Okay, but there exists a search space which is sorted or which is monotonic. Okay, so I will explain you what is the meaning of this term monotonic. So you must have heard about monotonic functions. Okay, let's say the functions which are increasing or non-decreasing, or let's say this kind of a function is also a monotonic function. Okay, so that means that function is either non-decreasing or it is non-increasing. Okay, So we will find a search space for this problem that is monotonic, and we can actually apply binary search on that particular search space. So this concept of search space is common for all problems. So most of the problems which can be solved using binary search will have this concept of monotonic search space. Okay, so clearly if you're given a number n, you can say the square root of that number can lie in this range 0 to n. Okay, so this is actually true because for any number, let's say that's 1. So for any number that is, let's say 1, you know the square root of 1 is 1. Okay, so the maximum value of the square root can be the number itself and the minimum value can be 0. Okay, but let's assume square root of a number will lie in this particular range. Okay, and for example, let's say we take n equals to 50. So we will say, okay, the square root of 50 will lie in this particular range 0 to 50, and we can apply binary search on this range, because if I find the midpoint is 25, and at midpoint I have to make a decision whether to go left or whether to go right. So that's what I need to do. So how I will make that decision? So we will make a function that will check if this midpoint can be a square root of 50. So clearly in that function we will check the value of 25 square. So we'll see 25 square is obviously greater than 50. That means all other numbers which are greater than 25 cannot be square root of 50. So this is the monotonic property. That means 25 cannot be square root of 50. So that means all other numbers between 25 to 50 cannot be square root of 50. So we let's make something like a number line, and we say, okay, after 25 we have everything as false. Okay, so I just put everything as a false. Now I will find out the next midpoint that is in this region. Let's say this is 12, and I can check if 12 is the square root of 50. If 12 square is greater than 50, yes, obviously that means all other numbers in the range 12 to 25 cannot be the square root of 50. Okay, so we put everything as false here. Okay, so this part of the array is discarded. So I actually need that value where I will get a true. So I have this range now 0 to 12. So okay, so I have this part of the array that is now 0 to 12, and I will find out the next midpoint. Let's say that is 6. Okay, so at 6 I will check, can 6 be a square root of 50? Okay, now you know 6 square is less than equal to 50, that is 36. So 6 can be a potential answer for the square root. So we will keep a variable answer and we will update it as a 6. Okay, so although 6 is not the square root of 50, but 6 can be a potential member, because we are looking for a floor value. Okay, so we are looking for a number whose square is less than equal to 50. Okay, we have 6 square, that is 36, this is less than equal to 50. We have 7 square, that is equal to 49, that's also less than equal to 50. Now as soon as you get this number, your goal is to reach a number whose square is as close as 50. Okay, so at 6 you know this answer is true. So that would also mean all other answers before 6, they will be also true. That means all other members 0 to 6 can be potential square root of 50, but we will discard that part of the array because we want a larger number. Okay, we want the square to be as close as 50. So now we will reduce our search space to this. Now we again find out a midpoint, that is 8, and we see 8 square is greater than 50. So we discard this part of the array. Okay, we discard this part of the array from 8 to 12, and now we will have start and end in this range 6 to 8. We again try to find out the midpoint, that is now 7. Okay, and we see if 7 square is less than equal to 50. So we see yes, so we update our answer as 7, and if you keep on doing this, you will have start greater than end, and you will converge at this particular point. Okay, now on this number line, if I represent true by a value of 1 and false by a value of 0, you will see the graph would look something like this. You have lot of trues followed by lot of false. Okay, so although in this problem there was no such array given, but we came up with a monotonic search space. So this is the meaning of monotonic search space, and in all such problems you will have to find a point where the first value is true or where the first value is false. Okay, so these kind of points you may need to find out, and we will use binary search to find these points. Okay, so in our case this answer would be 7, and because 7 square is less than equal to 50 and 7 is the largest integer where this property holds or where this condition is true. So this is how we will apply binary search to solve this problem. So now let us quickly dive into the code and write this. Okay, so maybe let's call it as square root dot cpp. Okay, so you can make the function as int or float depending upon what you want, but we can also find out the floating part, so I can change that later. So I can say my search space will start from 0, it will end at n, and I can put while start is less than equal to end, I will try to find out the midpoint. Okay, so let's say float answer equals to -1, that means answer is not known. So we say okay, mid is given by start plus end by 2, or you can use right shift 1, that is also fine. And if mid star mid, okay, so it is possible that your number is a perfect square, so in that case this condition would be true. If the number n is 49, then if you converge at 7, you know the answer. Okay, so you return the midpoint. For all other cases, when mid into mid is less than n, okay, so in such a case, let's say you are at 6 square is less than 50, then you have to update your answer. You say answer equals to mid and you try to find a larger number. For that you need to move start equal to mid plus 1, otherwise your end will move to mid minus 1. That's it, and you can return the answer from this point. Okay, so that's it, and let's build the code and run from the terminal. So if I give the number as 100, I get the answer as 10. If I give the number as 50, I get the answer as 7. So I hope this part is true, and you can also find out the floating part by using a brute force approach, because that is not going to take time for this particular part. Okay, so what I am going to do, for example, you want to find the square root of 10, that is 3.162. so what you can do is you know the integer part. Okay, so that we have done using binary search. Then you can just keep on adding 0.1 and check if this is less than equal to 10. If it is yes, then you go to 3.2. 3.2 square is not less than equal to 10, so you go back one step and you make it as 3.1. Next time you make your increment that was initially 0.1, you make this increment as 0.01 and you add it, you check this is less than equal to 10, yes, so you go to 3.12. Less than equal to 10, you go to 3.13 and so on. Okay, unless this value is not greater than 10. So you keep on doing, and if you want the precision up to p places, you can repeat this loop p times. Okay, so I can quickly code this part as well. So let's say float increment equals to 0.1, and let's also change the return type to float. Okay, and here I can say for int times equal to 1 times less than equal to p, because I want to do it p times plus plus. So what I will do, I will see while answer square is less than equal to n. If it is yes, I will increment my answer. Okay, so once I come out of this loop, I know I have overshot the value of answer, so I have to come one step backward. That is done using answer equal to answer minus that particular increment. And also for the next place, you have to reduce the increment by a factor of 10. Okay, so that's it, and this should help us to solve this part also. Okay, so the overall complexity would be log n for the square root part, and it will be, this loop will work at most 10 times. Okay, because for every place you have digits in from the range 0 to 9, so this loop will run 10 times, and this loop will run p times, where p is a small number, let's say 5 digits or 6 digits. Okay, so it will be order of n log n plus 10 into p, or this can be written as order of n log n plus p. And p is a very small number because precision will have some 6 number of digits or 8 number of digits. Okay, so the overall complexity is almost, sorry, uh, log n, right? So binary search is going to take log n plus p, so it's not n log n, I just uh, write it by mistake, it's log n. Okay, so it's going to be log n plus p, and p is a small number, so it's going to be close to log n only. Okay, so let's see, let's give the precision as 3, and here I can get p also. So if I give 10, so I get this as my answer. If I get 2, okay, so you can see it's working fine, and that's how we could uh, code it. Okay. Hi everyone, so in this video we will discuss a problem, aggressive cows from Spotch. So very interesting problem, and also has been asked in a couple of interviews as well. So let's discuss what this problem is. So let's go it line by line. Okay, so it says there is a farmer who has a long barn, and in this he has n number of stalls. So the stalls are located on a straight line along the positions x1 to xn. So there is a stall in which you can place a cow, and the stall is located on a straight line. Okay, so the cow can be placed on the stall. So what you need to do is you have c number of cows, and you can see number of cows in the worst case can be same as number of stalls. Okay, so c is less than equal to n, but it's that basically means you have stalls greater than equal to number of cows. Okay, so cows don't like this layout, and they become aggressive towards each other. So if you place two cows close to each other, they get aggressive, and they want to maintain some distance. Okay, so each other to put into a stall, so we cannot put two cows in one stall. To prevent the cows from hurting each other, we want to assign the cows to the stalls such that minimum distance between two of them is as large as possible. Okay, so what we need to do is we need to maximize the separation between every two cows. Okay, so suppose you are placing the cows along this distance like this. Let's say this is at x coordinate 5, let's say this cow is at x coordinate 10, and let's say this is at x coordinate 12. So the minimum separation between these two cows is 5, and between these two cows is 2. So for my question the answer would be 2. Okay, so the minimum separation between these two cows is 2 in this case. So we have to come up with such a placement that maximizes this minimum separation. Okay, so we have to maximize this distance. Maybe we shift this cow one step this side, then we will have a cow at x equal to 5, a cow at x equal to, let's say, 9, and a cow at x equals to 12. So we will have a distance 4 here, and we will have a distance 3 here. So in this case a maximum distance is 3. So this is a better configuration than this one. So this is what we need to do. So let's go through the input format also. So in the input I am given, I have one test case, I have 5 stalls and 3 number of cows, and these are the locations of the stalls. These are the x coordinates. Okay, number of stalls, number of cows, number of test cases. Okay, so let's try to visualize this, and let's see how we can get the output for this test case. So there is a stall at x equal to 1. Okay, and let's say there is a stall at x equal to 9, there is a stall at x equal to 2, there is a stall at x equal to 4, there is a stall at x equal to 8. Okay, so these are the locations of the stalls. Okay, and we have to place 3 cows. Okay, so what we can do is we can start placing cows one by one. So let's place the first cow at this location like this, and for the second cow we can maybe we can place a cow like this. Okay, and maybe third cow is like this. Okay, but this is obviously not the correct answer. Okay, so we have to do something such that these cows are as far as possible. So we, if we do a brute force kind of a thing, if we try out all possible combinations, it will actually take a lot of time. So it will take the complexity NC. Okay, so this is for combinations. Out of n stalls you have to choose c number of stalls for the cows. Okay, so that is going to take a lot of time. Okay, so we have to think something efficient and something better. Okay, so let's see how we can solve this using a efficient approach based upon binary search. Okay, okay, so let us have a look at two configurations. Let's, in the first configuration I place a cow here, and the second cow at this place, and let's say the third cow at this place. Okay, so this distance is 4 minus 1, that's 3, and this distance is 9 minus 4, that is also 5. Okay, so the minimum of these is 3, so I can say my answer is going to be 3. Okay, and in another configuration I can place this cow C3 at x equal to 8, so this distance will be 4, and still my answer would be 3, because we have to maximize the minimum separation. So this, in this case, minimum separation is 3 and we are maximizing it, and that's also 3. Okay, so if you place cows like this, okay, if you place here at 1 and at 2 and at 4, in this case the answer would be little less, because here this minimum separation is 1 and here it is 2. So sorry, the maximum separation between two cows here is 2, and if you see for all the cows this is 1. So between 1 and 3 you will obviously choose the second option. So this is the better configuration, and I don't think we can do better than this in this example. So let me show you. The output is also 3. Now we have to arrive at the solution. So how do we arrive at the solution? So solution is, you need to think of an answer first. Okay, you need to think what can be a possible answer. So let us think of a search space in which this answer can lie. Now, you know, if you place two cows in the same stall, the minimum possible answer would be 0. And if you do not, if you place two cows on the extreme ends, okay, so the maximum possible separation would be 8. Okay, 9 minus 1, that is 8. So that is the difference in the distance of the last stall and the first stall. So in this case, what you will get something like this. You will get a hypothetical number line that I'm calling it a search space, and you can apply binary search on this line. Okay, so why we can apply binary search on this number line? Because you will have something like this. So if I say you can place a cow at a distance k, so I'm saying if you can place all cows with a minimum separation of at least k, it also means you can place all the cows at a minimum separation of less than k. Okay, so that what I'm saying is if you can ensure that the minimum distance between any two cows is 3, that means you can also ensure the minimum distance between any two cows is also 2, is also 1, it's also 0. So I can say for this part of the array, okay, my answer is going to be true, and for maybe some other part of the array my answer is going to be false. Okay, so this is like a monotonic function. Okay, and this is, let's say, the separation, and this is the value of the function. I will explain it in more detail. So why we can apply binary search, because this search space is going to be a monotonic search space. So let us discuss this in more detail, and that will actually help you to uh, clear out the idea more. Okay, so let's discuss. So what I am saying is, assume a hypothetical number line in which you have a variable separation that denotes the minimum separation between two cows, and we know this separation can lie in 0 to 8. But let's say this is my starting point and this is my ending point. I try to find out the mid. So mid is going to be 4. So I need to ensure, is it possible that two cows are placed at a distance which is less than this distance? Okay, let's say this mid is equal to 4. Okay, so I need to come up with a configuration such that I am placing cows such that the minimum separation between two cows is at least 4. So this is my stalls: x equal to 1, x equal to 2, x equal to 4, x equal to 8, and x equal to 9. So let's try to see if it is possible to place all the cows on the stalls with a minimum separation of at least 4. That means if I place the first cow here, I cannot place the second cow here. I cannot place the second cow here because this distance is 3. I can place the second cow here, and I cannot place the third cow here. Okay, so that means my answer is going to be false. Okay, so if I cannot place two cows at a distance of 4, that means I cannot place them at a distance of 5, 6, 7, and 8. So we will discard this number line. Okay, so this number line represents the separation or the distance. So we will try to reduce our search space from 8 to 4. Now what we will do, we will find out mid in this. Mid is 2, and I will check if it is possible to uh, place these cows on the number line such that, on the stalls, such that minimum separation is at least 2. So let's do it. I've placed the first cow here. I cannot place the second cow here. I can place the third cow here, second cow here. I can place the third cow at this location. Okay, so that means my answer is going to be true. It means if I can place all the cows at a minimum separation of at least 2, that means I can also place them at a minimum separation of 0, 1. So I will discard this number line, and I will now try to find out my answer in this particular range. So the answer is true. So whenever you get answer as true, you keep a variable called answer that will actually update whenever you get a true. Okay, so let's say my answer is 2. So that means I can ensure at least 2 separation till now. So now if I try to find out the mid, I will get the mid as 3, and I have to check, can I place the cows such that the minimum separation is at least 3. So if we do it like this, first cow at this stall, second cow cannot be placed here, second cow can be placed here, and the third cow can be placed here, because at these coordinates the minimum separation is at least 3. That means I will update my answer, and this is going to be 3. So eventually, doing these steps, you will converge at a single point where you will get a true value. Okay, so what will happen if you try to visualize this from, let's say, 0 to 8? Okay, you have a point 3 where you are getting all values as true, and after 3 you are going to get all values as false. Okay, so that's like a monotonic function. So what we needed to do is, or you can say false is like 0. Okay, so all truths have the same value. Let's say true is denoted by 1 and false is denoted by 2. So this is like a monotonic function, and what you needed to do is you needed to find out this particular value where the last true is coming, okay, or the largest value where the true is coming, okay, where the configuration is possible. So that's how we have used binary search in this problem, and we came up with a search space that is monotonic. Okay, so you actually won't be given arrays in all the problems. You have to find monotonic search space in such problems. Okay, so now let's see how we can write the code for this particular problem. So let's quickly dive into the code and see what we can do here. Okay, so the first step is to you need to take input stalls and you need to sort this array. So I've just made a small test case from the input and I've written it in the sorted order, and here we will now write our binary search algorithm that we just discussed. So we need to assume a hypothetical search space that starts from 0 and that will end at stalls of n minus 1 minus stalls of 0. Okay, so this is our search space, and let's assume the maximum answer or the maximum separation is 0 as of now, and we can do while start is less than equal to end. We can find out the midpoint. So midpoint will be given by start plus end by 2. So remember, we are not applying binary search on this array, we are applying binary search on this search space. That is quite different. So after that we have to write a function that if it is possible to place the cows at this minimum separation. Okay, so this is the minimum separation at which we want to find out. So I can say bool can I place these cows. So I make a variable cows rug pi. So this will make a function call to another function that will check if we can place the cows. Okay, so bool can place cows is a function that will get the number of stalls, the number of cows, and the minimum separation that we are checking. Okay, so we will come to this function later on, but this function will return true or false, we will see. So let's make a call to this function can place cows. I give stalls n, the number of cows is cows, and the minimum separation is mid. Okay, now in this function I will get a true or false value here. Okay, so if this variable is true, if cows rug pi is true, that would mean I can make my answer larger. Okay, for example, if the minimum answer is 3. Okay, so what we actually want to do is we want to maximize this minimum answer. So we will try to check, can we make it 4 or 5 or something like this. Okay, so if this is true, so we will make our start point to mid plus 1. Okay, so that's what we are going to do. So we will update our answer because we got a true value. So at least this much answer we have, and start will be equal to mid plus 1. Okay, so we may or may not get true next time, but we will have at least this much in our answer. Okay, so else we can say and equal to mid minus 1. So simple binary search is what we are doing, and finally you need to see out the answer. Okay, and now we will try to complete this function where we can see if we can place the cows or not. So what we can do, we can say where is the last cow that we placed is at stalls 0. So that means we are going to place the first cow in the first stall. Place the first cow in the first stall. So that is actually needed because if you want to maximize, then you must occupy the first stall in the row. Okay, so for all other stalls, that is I equal to 1, I less than n, I plus plus. So this is starting from the second stall. We can see if I can place a cow at the second stall or not. So for if stalls of I minus the position of last cow is greater than or equal to the minimum separation. If this is the case, that means I can place a cow at that location. So last cow will be placed at stalls of I, and we can say, okay, let's maintain a variable called count, how many cows you have placed. So that will also increment the count. The number of cows you have placed is incremented by 1, and if this count at any point becomes equal to C, that means all the cows have been successfully placed. You can return true, otherwise you can return false from the end of this function. Okay, so let me dry run what we are doing. So let's say you have this number line, you have this stalls number line. Okay, so you have stall at 1, 2, 4, 8 and 9. Skip this one. So let's say last cow is at this, so C1 is here. Let's say minimum separation is 3. We want to check if there is possibility to place all the cows at a minimum separation of 3. So stalls I minus last cow is greater than equal to minimum separation. So I go to the next stall, I see if this coordinate 2 minus 1 is greater than equal to 3. No, it is not. So we just skip this if block, we go to the next. We go here, we check 4 minus 1, that's 3 is greater than equal to 3. Yes. So what we will do, we increment the count. So we place a cow here, and we also say last cow is now placed at stalls of I. So we say, okay, this is the last cow where we have placed. We go to the next stall, we see, okay, if 8 minus the last cow, that is at 4, is greater than equal to 3. Yes. So we place a cow here, C3, and at this point the count becomes equal to 3, so we return true. So that means for 3 this is the configuration, and we are able to place the cows successfully, and we will try to look for a better number, that is 4 or 5. So that's what we do here, start equal to mid plus 1, but we won't get such a number in this example, so the final answer should be 3. Okay, so I have built the code, and let's try to run this one. Okay, so I'm getting the answer as 3. That means our solution is correct. And that's all for this video. Thanks a lot. Hi everyone, in this video we will discuss another problem that's called book allocation from hacker blocks. So let's go through the problem statement and discuss this problem. Okay, so it says you're given number of pages in n different books and m number of students. Okay, the books are arranged in ascending order in number of pages, which means there is an array of books, and each book has more pages than the previous book. Okay, and every student is assigned to read some consecutive books. So each student will read a small segment of books, but it should be a continuous segment. The task is to assign books in such a manner such that maximum pages assigned to each student is minimum. Okay, so I will explain you with the help of one example. Okay, so I have one example here. So for example, let's say you have 4 books, so you're given n, and let's say these are the number of pages in each book. So this is book B1, B2, B3 and B4. So what you need to do, you need to divide the books into 2 students. So m can be any number, 2, 3, 4. Okay, so maximum there can be 4 students, because to each student you will assign at least 1 book. That's what you will do. So question is, you want to minimize the maximum pages that are assigned to each student. Okay, so let's see with the help of this example. So you have, let's say 4 books, 10, 20, 30 and 40. So you have to divide a continuous segment of books among 2 students. So maybe you can say, okay, this is one segment, this is another segment. So in this case, the first student will be reading 30 pages and the second student will be reading 70 pages. Obviously, the maximum pages a student is reading is going to be 70 in this case. Okay, another option could be, you can say, okay, first student will read 10 pages and second student will read these many pages, so it's going to be 90. So the maximum pages that a student is reading in this case is actually 90. Okay, a third option would be, you can say the first student will read the first three books, that is 60 pages, and the second student will read 40 pages. Okay, so that's like 40 pages. So in the third option the answer is going to be 60. So in all of these cases, if you minimize the maximum number of pages for each student, that is 60. So we can say in the worst case or in the best case, no student is reading more than 60 pages. That's what is the final answer for this problem. Okay, now you may think how we can solve this. So clearly, if it would have been only two students, the approach could have been different. But since we can have variable number of students, the brute force approach would be something like this. Okay, so brute approach would be, if you have n positions, so if you want to make divide this into three partitions, let's say you want to divide in three students, so for that you will actually place two number of bars to divide this array. Okay, so in how many ways you can place a bar, but in n places you can place a bar in n(c)m minus 1 ways. Okay, and this is going to take a lot of time, because lot of combinations can be there, and for each combination if you try to compute the answer, it's going to take lot of time. Okay, so that's going to be n into something. Okay, so NCR is like this: n into n minus 1 into n minus 2. So it's going to do kind of an exponential. Okay, and similarly 1 into 2 into up to r. So a lot of combinations can be there, so that's not a very feasible approach in this problem. So let's think of something else. Okay, so there is a big hint in the question: the books are in the sorted order. Okay, so if the books are sorted, so can we exploit this property to do something else? Okay, so let's see if we can use binary search, and can we think of a monotonic search space. Okay, so what we can do is we can actually do something like this. So let me yeah, so let's do one thing. We have 10, 20, 30 and 40. Let's try to find what is the minimum pages. Okay, answer is the minimum pages. So what can be the minimum pages in the worst case? So in the worst case, or in the extreme case, a student is not reading any pages, that is 0 pages. And in the worst case, a student would be reading maximum pages would be all of the pages. Okay, so all of these pages, that is like 100 pages. Okay, so that's what we can do. Or we can also start with 40. The minimum can be 40, because if there are m students and a student will read at least one book, so if a student reads at least one book, he will read at least 40 pages. Okay, so out of all the students, one student will be reading this book, and you can say the minimum will be at least 40. That's what you can say. You can say start is equal to 40 and end is equal to 100. So you can pick start as the largest number of pages in any given book, and end is, let's say the student is reading all the pages. Okay, so I will just write it again. So it's 40 and it's 100. Or you can also take 0 and 100, that's also fine. And we will try to find out a midpoint. Let's say mid is 60, 70. Okay, so now I want to check if it is possible to make a configuration in which no student is reading more than 70 pages. Okay, so what I will do, I will take some students and I will start allocating them some books. Okay, so I have this array 10, 20, 30, 40, and I say okay, take student 1, and I have to make sure that no student reads more than 70 pages. That's my limit. So I give him the first book, read 10 pages. He says okay, I can read. I give him the second book. He says okay, I can read. I give him the third book. The total is still less than 70, so I keep on giving him more books. So now this total is 60. So can I give him more pages? No, obviously I cannot. So he is reading less than equal to 70 pages. let's take another student and give him the books after the 30th, this book, okay, after the B3. So I say, okay, you read 40 pages. He said, okay, I can read because I have to read less than equal to 70 pages. So I'm assuming if 70 can be my answer, obviously yes. So I get a true value at this point. Similarly, it will be true for all values greater than 70, okay, because if it is possible to make a configuration in which student is reading less than equal to 70 pages, it is also possible to make a configuration in which student is reading more than 70 pages, okay. So that's the whole idea. So what we can do next is we can now reduce our search space to this part, and we can again find out the midpoint. Now let's, the midpoint is 55. So now I will again ask all the students, can we come up with a configuration in which no student is reading more than 55 pages. So I pick the first student, S1. I give him 10 pages. He says okay. I give him 20 more pages. He says okay. I give him 30 more pages. He says I'm not okay because I cannot read more than 55 pages. So I pick student S2. I give him 30 pages. He says okay. I give him 40 more pages. He says not okay because I cannot read more than 55 pages. So I pick a third student, and as soon as I pick a third student and give him 40 pages, this violates my condition of the problem that there are only two students in this case. So I cannot take three students to assign these pages. So that means 55 as a configuration or 55 as an answer is not valid. So this is going to be false, okay. So it means it is not possible to make a configuration in which student is reading less than 55 pages, okay. So we will have false for everything here. Similarly, we will reduce our search space between 55 to 70. We will try to find out the midpoint, and let's say this midpoint is something x, okay, let's say 62 or something. Now you will again check, let's say this point is 62, okay, because 70 plus 55 is 125 and it will be around 62, yes. So can we make a configuration in which no student is reading more than 62 pages? Obviously yes. So first student will get 10 plus 20 plus 30 and second student will get 40, and in both cases it is less than equal to 62. So that means our answer is true at this point. So we keep on reducing this search space and you will see eventually we will converge at 60. We will finally converge at 60. So this is the whole idea. So in all binary search questions, okay, you will first find out the search space, and the search space will depend upon what you want to output. If you want to output the minimum time, so search space will be on time. If you want to output the minimum number of pages, the search space will be on pages, okay. So that's the whole funda in every binary search problem. I think the logic is clear, and now we can easily write the code for the problem, okay. So let's see the code. Hey guys, now I will write the code for the problem, book allocation, and let's go through the steps that are needed to implement this problem. So first of all, I need to input the number of test cases as given in the question. I take input the test cases, and for each test case I need to input the values of n and m. So I say okay, I have n and m, so I do scene m and scene m. Then I also need to declare an array, and that should be, let's say, let me check the constraints. So look, in number of that can be a small array. All right, so let's make a smaller array, and for each case we need to input how many pages are there in the book. So scene array of I or array of j, this should be j, okay. And let's make a function that will actually help us what is the minimum number of pages that we need to read in this case, okay. So this find pages will be a binary search algorithm that we have discussed. So we have the array, we have the n, and we also have the m. So let me make a variable called int sum equals to 0, and I can make some checks. Okay, so as given in the question, if n is less than m, then we have to print -1. So that means no such configuration is possible, so return -1. And for other, I need to count the number of pages also. Okay, so we will do two things. um, because we want to find the start and the end. Okay, so starting is will be given by array of n minus 1, and end will be equal to sum of all pages. So we can just find out that particular sum by iterating over the array. Okay. So how many total pages we have in all the books? So I can say sum plus equals to array of I. Okay, so maybe I think this should be okay. And if the constraints are large, you may take this as long, but for this problem they are not really required. Okay, so you can say sum of all pages, that's equal to sum. Okay, now we know the start and the ending point for the binary search. We can put our loop while start is less than equal to end, and we will try to find out the midpoint. So midpoint is start plus end by 2, and here we can make a function if it is possible to divide the books in the array among m students, and such that no student is reading more than mid number of pages. If this is the case, we will update our result. So let's assume our initial answer is going to be int max, and I can say answer is going to be equal to whatever is the minimum of my old answer and my current answer. Okay, so my current answer is going to be mid. I can update it, and we can try to reduce the number of pages. So remember, in this case we are having something like this. We have lot of trues and we have lot of false. So at one point 60, we know that it's possible to read all the books, or divide the books such that no student is reading more than 60 pages. For values less than 60, it is not possible. So we have a monotonic function. So if you are at this particular point, let's say 80, then you will try to reduce it to 60. So we will make end as mid minus 1. Okay, otherwise we can make start as mid plus 1. So that's the whole idea of binary search. Okay, so again, so this is the case when it is not possible to divide at x pages. So that means you have to increase the number of pages, and finally you have to return the final result or the final answer. So return the answer. Now our task is to write this function is possible. Okay, so let's go write the code for is possible. Bool is possible to divide the books array with this minimum. So we have the current minimum, that's okay. So what we will do, we will take the first student. So let's say student used is 1, and int how many pages this student is reading. Okay, pages that the current student is reading is equal to 0, and I will iterate over all the books I less than n I plus plus. And what I will do is, if let's say my current minimum is 30, let's say, okay, so now you can have a case, you won't have this case, right? Okay, so I was thinking of something, but that's fine. Okay, so I was checking, do we need this check? If array I is greater than current minimum, then return false. Okay, so this is actually really not required, because we are starting with a search space in which start is going to take a value of the largest book. So that means all values in the search range start to end will not will follow this condition that array I is less than equal to the current minimum. Okay, so this is not really required, so we can skip this step, and we can now make a running sum. Okay, so if pages that a student is reading plus the current book, that is array of I, is greater than the current minimum, if this happens, then we will need a new student. So student used will be plus plus, and the pages that the new student is reading will become equal to array of I. So let me explain this, and before that I will complete the code. Okay, if students required used is greater than m, I will return false. Otherwise I should keep on adding the pages to the current student. Okay, so very small piece of code, I will just explain you what I'm doing here. Yeah, it should be fine page. Okay, so now guys, let's have a look what I just did here. Now assume you have this books array that contains 10, 20, 30 and 40. Okay, and I say okay, the count of my let's say the current minimum is 60. I want to see if 60 is a possible answer or not. Okay, so I say okay, I will take the first student. So student uses 1. How many pages he is reading? 0. I iterate over the books array. I go through this array. I say okay, pages reading plus array I. If this is greater than the current minimum, so 0 plus 10, is it greater than 60? No. Then I say okay, increase the pages of this student. So this student is now reading at least 10 pages. Then I again go to the next position. I say if I add 20 to this, is it greater than 60? No. Increase the count. So this student is now reading 30 pages. I go to the next position. I say okay, add 30. So if 30 plus 30 is greater than 60, no. So I increase the count of the student to 60 pages. So every time we are executing a else block. Now finally I go to the next position. I say okay, 60 plus 40, can I assign 40 more pages to the student? Yes, it is greater than 60, so I cannot do this. So I come in this condition, I increase the student count. So I go to the next student and I say pages that this student will read will be equal to array of I. So that means the first student will read only 60 pages and the second student will read 40 pages. And let's say if I have more, like 10, 15 or something, I will now give the next 10 pages to the student. I can see, can he read 10 more pages? If this is greater than 60, no. I come in the else block. I say okay, this student will read 50 pages. Can he read 15 more pages? Is it greater than 60? Yes. So he will not read these 60 or 50 more pages, 10, 15 more pages. I take the next student S3, and as soon as the number of students used becomes greater than the value of m, I return false, which means this is not possible. Okay, so this is how we are writing this function as possible. So I hope it is clear, and that now I will show you if it runs fine on the given example. Okay, so let's maybe try to submit this. So I will also run it locally on the int max. So one test case, I have n and m, so I have 4 books, 2 students, 10, 20, 30, 40. So yes, I'm getting 60 as the answer, which means it should be correct, and it has also passed all test cases on HackerBox. So which means our solution is correct, and I hope you got an idea how do we approach this kind of a problem. Thanks a lot. See you guys in the next video. Hey guys, in this video we will discuss a very interesting problem, Prata from Spoj, and let's go through the problem statement. So it says there is a meeting going on, and the manager wants to serve cheese paratha after the meeting, and people have asked to order some pea parathas packed for the function. So the requirement is to get an order of pea parathas, and the stall has L number of cooks. Okay, so there are some number of cooks who can cook the paratha. Okay, so there is a cook C1, there is a cook C2, and there is a cook C3, and there is a cook C4. So they can have a rank. Okay, so each cook has a rank. Let's say he's a rank 1, he's a rank 4, it is a rank 2. A cook with rank R can cook one paratha in the first R minutes, one more in 2 hour minutes, one more in 3 hour minutes, and so on. Okay, so if you want to get 4 parathas from the cook with rank R1, how much time it will take? It will take R minutes. Okay, so if the rank is 1, so that would mean if you want to make 4 parathas from this cook, he will take actually 1 minute for first, 2 minutes for second, 3 minutes for third, and 4 minutes for fourth. That is 4 plus 3, 7 plus 2, 9 plus 1, 10. So it means this cook will cook 4 parathas in 10 minutes. Okay, and so on. So the webmaster wants to know the minimum time to get the order done. Okay, so you are given the number of cooks who are going to work in parallel, and you need to know how much total time they will take to make an order of pea parathas. Okay, so that's what it is given. The first line gives the number of test cases. Each test contains 2 lines, and in the first line of the test we have the number of parathas to be ordered. Okay, and then you have a number of cooks L, and followed by the ranks of cooks. All right, so what you need to do, you're given like this. You have 3 test cases. In the first case you need 10 parathas, you have 4 cooks, and these are the ranks of the cooks. Okay, that's what is given to you, and you need to find out how much minimum time they will take to get these many parathas. Okay, now again we have to think what is the time. Okay, so here you need to output the total time, the minimum time. Okay, and can I think of some bounds in which this answer will lie? I can say, okay, the minimum time can be 0, and the maximum time will be, let's say, infinity. Okay, or let's say 10 power 18, that's infinity in C++, the largest number. Or you can say it will be the time taken by the slowest cook, or you can also say time taken by the fastest cook himself to make these parathas. Okay, so that's what you can take as the maximum time. Okay, that's what you can say. Okay, I'm sure that at least in this much time the fastest cook can make all these parathas. Okay, but since multiple cooks are going to work in parallel, your exact answer will actually lie in this particular range. Okay, so maybe you can start with any upper bound, so it can be infinity, that's 10 per 18, or you can take time taken by the fastest cook, or you can take time taken by the slowest cook as well. Okay, so what you need to say, let's say you make a guess and you say it's 100 minutes, let's say time taken by the fastest cook, but actually it would be like this. It will be 1 plus 2 plus 3 plus up to summation of 10. So that is 10 into 11 by 2, that's 55. Okay, so actually this is 55, but let's say it's 100 minutes. Okay, so now what you want to do is you need to check, you can apply actually binary search. Why? Because if you find out the midpoint and you will check, is it possible to make 10 parathas in 50 minutes? Okay, you will write a function that will check that given 50 minutes how many parathas can be cooked. If the answer is more than 10 or equal to 10, then you will say yes. So let's assume in 50 minutes you can cook at least 10 parathas. So that would also mean for all these values of time that are greater than equal to 50, the answer would be yes. Now you will actually apply binary search in this part, okay, because you want to find the minimum time, so you try to reduce the time, okay. You see, okay, is it possible to get these parathas done in 25 minutes? Yes, we can make these parathas. So let's say this is also true. So you discard this part of the array and you apply binary search in this part. Next time you find out the midpoint. So can you get 10 parathas in 12 minutes? Okay, we have to check. We don't know. And I can see the answer is 12. So I can just verify. Okay, so how we are going to check, is it possible to make 12 parathas in 10 parathas in 12 minutes? So we will give 12 minutes time to each cook, 12 minutes to each cook, okay. So let's say we have a cook 1, we have cook 2, we have cook 3, we have cook 4. So let's see in 12 minutes how many parathas this cook can make. So first paratha in 1 minute, second paratha in 2 more minute, third paratha in 3 more minute, fourth paratha in 4 more minute. Can it make fifth paratha? No, because this will make total minutes as 15. So this means it can make 4 parathas, okay. And let's go to cook 2. He will take 2 minutes for the first paratha, 2 minutes have gone, 4 minutes for the second paratha, and 6 minutes for the third paratha. So how many minutes have gone? 12 minutes have gone, and he can make 3 paratha, okay. Let's go to the cook third, and let's see how many parathas he can make. 3 minutes for the first, 6 minutes for the second, 9 minutes have gone. That would mean it can make only 2 paratha. And let's go to the fourth cook. So 4 minutes for the first paratha, 8 minutes for the second paratha. He can also cook 2 paratha, okay. But we only need 10 paratha, and this sum is 4 plus 3, 7, 11. So that would mean this answer is true. So that means it is possible to cook 10 parathas in 12 minutes. So this answer is true. So we'll try to binary search on this part of the array, but this answer will be false, okay, because even if you give 11 minutes, then this cook will be able to make only 2 parathas, and this cook will be able to make 2 parathas, so you will only get 9 parathas in 11 minutes. So this answer is going to be false. So you can see this is a monotonic search space. You have everything as false till 11, and then after from 12 you have everything as true, okay. So our idea was to first find the first value where it is true, okay. So I hope you will be able to apply binary search on this problem and solve it, okay. So writing code for this problem is your homework, and it's a part of assignment as well, okay. So I hope you got an idea to approach this problem, and you would be able to solve it. Hi guys, in this video we will discuss problem winning CB scholarship from HackerBlocks. So let's begin with the problem. So it says Coding Blocks conducted a scholarship test, and it was decided to give 100% scholarship to the needy students. And in order to avoid any losses, Coding Blocks has n students and m discount coupons, okay. So to get a scholarship, a student will, okay, so there is only 100% scholarship that will be given, no other scholarship will be given. And to get 100% scholarship, x discount coupons are needed for one student, okay. So in order to get more discount coupons, it is decided to take y amount of discount coupons from students who performed badly in the test, okay. So we can give coupons to the students. If we want to give scholarship to one student, so we will give x coupons to him, and those students who perform bad in the test, they will give y amount of coupons to Coding Blocks, okay. That's what is given in the question. So good students earn discount coupons, whereas bad students need to pay coupons to get the admission, okay. So we need to say what is the maximum number of students who can get 100% waiver in the admission fees. So we are given 4 integers n, m, x and y, where n is the number of students, and where m is the number of coupons available. So these is the number of m is the amount of coupons that is available with us, okay. So we kind of an equilibrium. Okay, so we have to maximize the number of students who who can get the scholarship. Okay, so let's see the first example. So we have 5 students in this case, and m is the number of coupons here. Okay, and 2 is the number of coupons for each student that we need to give, and y is the number of coupons we can take. Okay, so let's see. We have 10 coupons, and for each student we need 2 coupons. So we have 5 students, and for each student we need 2 coupons. So if I want to give scholarship to all the 5 students, I actually need 10 coupons. Okay, and the availability of coupons is also 10, so that means all 5 students can get scholarship. So the output is 5. So do we have another test case? Okay, so another test case is not there, but we can generate. So let's say if we have 3 students and we have uh, let me see. Let's say we have 3 coupons, 3 students, and we have, let's say, m equals to 5 coupons. Okay, let's say student 1, and for each student, let's say we can have, let's say x is also 5. That would mean for each student we need at least 5 coupons. So using these I can give scholarship only to one student. So let's say y is 6. So that means I can borrow 6 coupons from the students. So in this case the answer will be 2, because student will get 1 will get 5 coupons. Student 2, for student 2 I have nothing left. Okay, so I don't have anything left with me, but I can borrow, I can ask third student to pay me 6 coupons, out of which 5 coupons I can give to the second student, and third student will not get any scholarship. Okay, so that's why the answer is going to be 2. Okay, so I hope you got the question at least, and now we have to maximize the total number of scholarships that we can give. Okay, so now clearly you can see in this question, uh, you want to output the maximum number of students. So can you think of a bound in which the answer will lie? Obviously yes. So that means the answer will be between 0 to n. And also, will this search space is a monotonic search space? Is it a monotonic search space? Yes, because if I say, let's say this is a point of where true will get converted into false. Let's say x is the maximum number of students. So that means if I can give scholarships to x number of students, I can also give scholarships to all other students which are less than x. Okay, so if I'm saying if it is possible to give scholarship to 10 students, then it is also possible to give scholarships to 2 students or 3 students or 4 students. And obviously if it is not possible to give scholarship to 11 student, then it is also not possible to give scholarship to 12 student, 13 student, and so on. Okay, so you will see this will have a curve like this. You will have all trues followed by all false. So you need to find out this point where the last value of true is occurring. Now we have to think of a criteria that will actually help us know that okay, this x is possible or not. Okay, so simply we want to check, is it possible to give scholarship to x number of students? That's what we need to check. Okay, if it is yes, we will try to increase the value of x by making start equal to whatever is x or mid. Okay, mid plus 1. If it is not, we will try to reduce this number by making end equal to mid minus 1. Okay, so increase the number of students if x is feasible, decrease the number of students if x is not feasible. We will apply binary search here. Okay, now how do we check if it is possible to give scholarship to x number of students? So x students will need how many coupons? Okay, so x students will need Okay, let me just take it something else. Let's say mid number of students will need how many coupons? So mid number of students will need mid into x coupons. Okay, where x is given in the question. These many coupons are required, and the requirement of coupons should be greater than should be less than equal to the available number of coupons. Okay, so how many coupons we will have with us? So we already have m coupons, and if let's say total number of students is n, and I'm saying I will give scholarship to the x number of students, that also means I can borrow coupons from the remaining students. Okay, so let's say these are the students who will get scholarship. I will borrow coupons from the remaining number of students. So the remaining number of students will be n minus x, n minus mid, and let me use the term mid instead of x here, okay, so that you don't get confused. So if I want to give scholarship to mid number of students, that means I can borrow coupons from n minus mid number of students, and each coupon will give me a y amount in the pocket. Okay, so the available amount or the available discount with coding blocks will have this much, because this is initially what they have, and from n minus mid students they can buy into y number of coupons, and this is required. If this condition is fulfilled, if this condition is true, we will try to increase the value of mid by making start equal to mid plus 1. If it is not, we will try to reduce the value of end by making it as mid minus 1. Okay, so this is how you should try to approach this problem, and the coding part is very simple. I would suggest you to try on your own and solve it. Okay. Hey guys, in this video I will show you another problem that's very popular interview problem as well. It's called painter's partition. Okay, so it's in the practice section in hacker blocks. So let's go through the problem statement, and I will give you a hint to solve this problem. So it says you have k painters and you have n boards, where each painter takes 1 unit time to paint 1 unit of board. Okay, so if there is a board whose length is 5 units, a single painter will take 5 minutes to paint this entire board. And similarly you have an array of boards. Okay, so it's a big array of boards, and you have to compute the minimum time to paint all the boards. And also every painter can paint only a continuous segment of the boards. A board can only be painted by one painter at maximum. Okay, so you cannot have two painters painting on the same board, but a painter can paint more than one board. Okay, so you need to think how to approach this problem and come up with the solution. Okay, so take 2 minutes, think, and pause this video here and think about the solution. Okay, so okay, let's discuss the solution. For example, let's say again the boards are like same, so it's slightly similar as book allocation problem. Okay, in that case you had to find the minimum pages, but in this case you have to output the minimum time required to paint the board. So you can actually do binary search on time. Okay, so minimum time, let's say if the board length is 10, 20, 30 and 40, so the minimum time required is obviously 40 because this is the largest board, and the maximum time required would be sum of all board lengths, because if a single painter is painting all the boards, the maximum time required would be 100. Then you find out the midpoint, and you say midpoint is 70, and then you can make a function, let's say check, to check if it is possible to paint all the boards in 70 minutes. Okay, so or you can check how many painters are needed to paint all the boards in 70 minutes. Let's say it returns the number of painters you will be needing. Let's say that x is the number of painters, and if this is true, okay, if this is true, that okay, so if actually x is less than equal to the number of painters available, so you return true, that this is possible. If let's say the number of painters given is 3 and you see 4 painters are needed, then it will return false. That means we will increase the time. Okay, so you need to increase the time if number of painters required is more than what is available. But if the number of painters required is less than what is available in the question, then you reduce your time. Okay, so try solving this problem using binary search, and it's very similar to the book allocation problem. So I will not show you the code, but I want you to try this problem yourself. Okay, and a similar problem that you must try is a problem from Spodge, and it's called eco. Okay, so let me give you the problem name, EKO. Okay. Yeah, so it's also a binary search problem. So definitely you should try both of these problems and try to come up with a binary search solution for both of them. Okay, so I'm not disclosing you the solution because I've already covered a lot of examples, and it's your time to think and analyze these problem statements. Thank you.